Okay, so we're gonna do some announcements before our Cyber Lab talk. So first thing, ACM Cyber is hosting our very own class. If you're not familiar with Engineering 1 courses, these are 2-unit courses that are hosted by the engineering department, and they're aimed to get students exposed to different topics within engineering. They are also easy A classes, which is nice. And so our Engineering 1 course will be focused on creating your own malware in Python, which I think that's pretty cool to create your own malware. So if you are interested, the class is now open for you to sign up, and it will be Tuesdays 3 to 6 p.m. Since this is an engineering class hosted by the School of Engineering, enrollment is restricted to engineering majors, unfortunately. However, as we have more people sign up for the class and as it gets closer to the start date, we can secure some PTEs for non-engineering majors. So if you're a non-engineering major and you're interested in the class, just hold out, just hold on, and we'll update you about that. Another thing is we are having a cyber potluck. It'll be this Saturday, at 6 from 6 to 9 p.m. at 910 Weyburn Avenue. We'll have lots of different foods. So if you are interested in coming to the cyber potluck, there is an RSVP form right here. So I'll give you all a minute or two to scan the QR code and RSVP. We will also be having a grocery run at 5 p.m. So if you don't want to buy groceries in advance or you don't know where to store groceries, that's completely fine. You can just come with us and we'll probably go to Ralph's, Ranch 99 and stuff like that. Okay, it looks like most of the phones are down. If you weren't able to snag the link, then it is this RSVP link is also in Discord announcements and I believe on the Discord event as well.
This Saturday, before the potluck, PBR will be meeting 12 to 5 p.m. Note this is an hour earlier than the usual time because we want to give a little bit of a buffer room between PBR and the potluck. As usual, it'll be in the E4 Tesla room, which is 53-125. Enzo will be giving a talk on cross-cache attacks, and TS will be writing some additional clone challenges as well. If you want some intermediate challenges to practice on outside of the CPM. Another thing that we're going to be doing is CCDC. So CCDC is quote a business-oriented system administration competition, but basically it is a defensive security competition. So the CTS we do are offensive security, right? You're given a service and you hack them. CCDC is a lot more about securing services. If you've done Cyber Patriot in high school, it's very similar to that. The qualifiers will take place on February 8th, which means that we will probably have to do a little bit of preparation over winter break. So if you're interested in participating in the competition, please fill out this form. And we can only send 8 people, so this form is not a guarantee that you'll be on the team. What? This is virtually. Quals are remote, but if we progress past qualifiers, the rest will be. Yeah, so for those who didn't hear, qualifiers are remote, but if we qualify for finals, that'll be in person.
That being said, when we say we will still be like, while it's a remote qualifier, you will still have to be in the room physically with the team for the competition.
Another thing are active membership requirements. So to become an active member of ACM Cyber, there are 3 different pathways you can go. I'm sure you've heard me yap about this before, but I just wanted to reiterate the requirement since it is nearing the end of the quarter. So to fulfill the active membership requirement for Cyber Lab, you have to create a blog post about your project and present at our symposium. We will give you time to craft your blog posts and your slides during the last Cyber Lab meeting, so don't stress about doing that outside of meeting times. And our symposium will be on Tuesday of week 10. I believe it is on the Discord events. So yeah, you are required to present at symposium, but if there is like some other circumstance, like maybe you're sick and you can't make it, just let us know and we'll make an exception within reason. But please do plan to be at symposium. It is also just really fun because you get to not only present all of your hard work throughout the quarter, but you get to see everything everyone else is doing, and we will have free food. So I think that is also a nice draw. Oh yeah. It will be 6 to 8 p.m., like the normal cyber meeting times, but that was a good question. Okay, with that, that is the end of the announcements, and I will hand it off for Arnav to do his talk.
All right, yeah, so my talk is going to be about Randar, and it's kind of like a pretty new exploit that people found out in Minecraft. Raise your hand if you ever played Minecraft before. That's a lot of people. That's great. So yeah, this is this is an exploit where you can, let me just show you. It's like, it uses Minecraft randomness in a very creative way. So Minecraft generates its worlds when you like walk around in a world, when you explore around, it generates them procedurally. So what you do when you generate a world is that you give it a seed or you enter a random seed. And based on that seed, Minecraft will do a bunch of math and just put a bunch of blocks everywhere. And specifically, whenever you load a new chunk, which is like a 16 by 16 area of blocks, whenever you like walk somewhere and you load a new chunk that you've not been in before, Minecraft will just do a bunch of math based on its surroundings and based on its random number generator to figure out what blocks go inside that chunk. But the way Minecraft randomness works, there's a lot of things you can actually do with it if you just peek into the math. For example, if you just look at a few blocks in a chunk, or like in here, you have a few cacti here, right? If you like look at the positions of these cacti and how tall they are, or if you look at this end portal and you see that it has all 12 Eyes of Ender pre-filled, based on that and based on like the coordinates that you are in, you can determine what the world seed is, even if you don't actually know what it is beforehand, just because of how the random number generator works. And there's even more crazy things you can do with it. So my talk will be about Randar, which is a new exploit people found around, I guess, 6 or 8 months ago, where you can find coordinate locations of other players on a server that you're playing on just by mining a block. So you take your pickaxe out, mine a piece of stone, and you just know where, I don't know, Joe is 10 million blocks away. You know his exact location. So it's kind of an insane exploit that people found out, and I'll walk you through it. So the first question we have to ask is, how do we make random numbers in the first place? A computer can't just generate a random number from software alone, because that's not how software works. So the way that computers generate their random numbers usually is through PRNG algorithms or pseudo-random number generator algorithms. So what these algorithms do is that you first give them a seed, and then they do a lot of like mixing math operations, whatever, to that seed. And you can keep asking a PRNG algorithm to give you new random values. You can say, I want a random value. I want a random value. And you just keep asking it. You keep asking it, and it'll give you more and more random values. The way it does it is that they store an internal state, which is like, I don't know, 64 bits or 128 bits of whatever. And when you ask for a random number, first they'll do some operation to that state and give you the random number. And then they'll change their state into a new state based on some other math operation, so that you can keep asking it for new random numbers. So this is how computers generate random numbers with software. But since these are not actually random, because basically if you know the state of a PRNG, you know every single random number it will generate in the future. So that property is called that is deterministic. And that's why it's not truly random. It's because there's an amount of information you can have such that you know every output it will say in the future. So to generate true random numbers, you have to use hardware. So for example, like random noise in like circuits or clock drift or cosmic microwave background radiation. These are all like sources of random noise that are actually truly random, it's literally impossible to predict what values they'll predict or what values they'll say because of like physics or something. But we're going to be talking about PRNGs today. So within PRNGs, there are two types. Just because PRNGs are deterministic doesn't mean that they're not useful. For example, we have general purpose PRNGs, which are used to be fast. They're very simple, and they approximate randomness to an acceptable degree. So whenever you like do math.random in like Java or JavaScript or import random.randint in Python, this is what's going on because you don't really care about it being perfectly random as long as it looks good enough and it runs fast, and that's fine. But that being said, there's also cryptographically secure PRNGs. And the difference with these is that they're indistinguishable from randomness, which what that actually means is that if I was given the output of a cryptographically secure PRNG versus actual randomness, and if I was asked to tell them apart or like tell which one was the true randomness, I couldn't do it. Unless I was like, I don't know, like unless I knew the internal state of the cryptographically secure PRNG. But if I had no information, and I was just relying on like my pure math ability, I guess, I wouldn't be able to tell them apart. So these are actually quite useful for like cryptographic applications because while they're still deterministic and they're still like pseudo-random, they look random enough such that no one can really tell the difference. So the random number generator that's used in Minecraft, well, specifically in Java, but then it's also used in Minecraft because Minecraft runs on Java. It's called an LCG. So when you type math.random in Java, it runs this random number generator algorithm called an LCG. What it does is that it has an internal state xn over here. And to go to the next state, what it does, it multiplies xn by a, adds c, and then takes modulo some number m. So that's the equation here. It's like you apply a linear function to it, and then you take modulo m. And that's the next state. To actually output the random numbers, you just output what the state is. Some interesting properties about LCGs is that they're periodic, which means that after some amount of asking it random numbers, it'll start repeating itself. And the period is usually fairly small compared to m. And also, if you know an LCG state and you know its coefficients, like you know what a and c and m are, you can easily go backward and forward as many times as you want. So knowing the state of an LCG basically means you completely crack the randomness of the algorithm because you know exactly what it'll say 5 times in the future, 10 times in the future, 15 times in the future. Does anyone have any questions about LCGs or randomness? Because yeah, I'm going to be talking a bit more about the math. Yeah. So yeah, that's a good question. So usually what people do for the seed is that they take the seed, they like transform it a little bit, and then they shove it into X0. So like you take the seed, maybe do like, I think they do like seed XOR some random value. Like by random, I mean just like some hard-coded constant, and then they shove that into X0. So the seed is kind of like the first state. You have a question? Good question. Linear congruential generator. So linear is because you're like applying a linear function. Congruential is because you're taking mod m, so that's called a congruence, and it's a generator. Any other questions about how this works? Yeah? Yes, they should be constants. Like if you actually look this up for Java, it'll tell you what the exact values of a and c and m are. But like, yeah, they're constants, but you can choose whatever you want for them. More questions? Okay, cool. So how are we going to attack insecure PRNGs? So in the simplest case with LCGs, when you ask for a random number, it's just going to tell you the state of the LCG. And that's really all we need because if we know the state and we know the coefficients, which are hard-coded into Java, we know all the future states. But that's not usually what happens. What usually happens is that we don't get all the full output of the LCG. We only get like, I don't know, the upper 10 bits, the upper 15 bits. So if the LCG outputs a 64-bit number, we can only usually see the upper 15 bits of it, and we don't know what the rest are. But that's good enough for us because what we can do is observe constraints on the output. And what that means is that basically, if we know that the upper 15 bits or the upper 20 bits or the upper 23 bits are some sequence, we can provide an inequality on the LCG state. It's described here. I'm not going to explain exactly how this works, but basically all you do, it's like you add a lower bound and an upper bound based on the values that you observe from the LCG or the known bits that you observe from the LCG. And this is a fact that you can say about the LCG state based on your observation of it. Yeah, I don't want to like explain this in super detail. Just know all you need to know is that you can create inequalities on these LCG states. Any questions on this? Okay, I'll go to the next one. So, anyways, how does that help us? What do these constraints help us do? So what we can do with these constraints is kind of put them in a thing called a lattice. So a lattice is like an n-dimensional vector space if you've taken linear algebra, but with only integers. If you haven't taken linear algebra, think of like, I don't know, a cube, but then you take like the corners of a cube and then you just kind of like repeat them over and over again. So it's kind of like 1, 1, 0, 0, then 2, 0, 0, but then that for like all 3 dimensions. So it's just a bunch of integer points in some space. It can be 3-dimensional, it can be 4-dimensional, it can be 18 gazillion dimensional. Doesn't really matter. It's just that it has to be integer points that kind of repeat themselves like this. And interestingly, LCGs are very closely related to lattices because we can represent all of these LCG states, LCG outputs as a point on the lattice or a vector in the lattice. Like you can say this vector over here is one possible sequence of outputs of the LCG, just like represented as one single point on the lattice. And what that allows us to do is that all of our constraints that I was talking about before, with all these inequalities, you can kind of create a box in the lattice where you know that your LCG outputs have to exist. So your constraints create a box here. If you guys see like the rotating thing, the red box is kind of the space of all possible seeds that satisfy our constraints. And we see that there's exactly one point inside that box, and that point is the one we're looking for. It's the correct seed that matches our constraints. So the hard work is actually to find that one point inside the box. In 3 dimensions, it looks really easy. Once you get to like 12 dimensions or like however many dimensions, it's actually a pretty hard problem. But there are algorithms that help you out, like LLL, lattice reduction, simplex, Babai, and some other ones. This is the kind of like a more advanced topic, but if you want to talk more about it with me, feel free. I've been looking at this stuff for a bit and it's really cool. But basically, once you find that point inside the lattice, that point tells you the LCG state that you're looking for. And once you know the LCG state, like I said before, you can predict any past or future value of the LCG. So that's kind of like golden, but that's what you're looking for. So this is the last math slide I'm going to talk about. So anyone have questions about this? Yeah?
Periodic, would it be possible to balance?
So the periodicity is not really important here. It doesn't have to be periodic, although it is. The important thing is that the LCG is linear. So when it's a linear congruential generator, that's why we can create lattices like this, because they're just, as you can see, you can just draw a bunch of lines on them. So that's the linearity is the important part. Any other questions? Yeah.
3 dimensions set against.
I didn't explain that, but in this box it says seed, next seed, and next seed of next seed. So basically, in this demo, the 3 dimensions are like the current LCG state, the next one, and then the next one after that. When you're doing these kind of like lattice problems, sometimes the dimensions will represent something a little bit different. But the idea is still the same, where you have to find a point inside the box. Okay, move on to the next slide. So that's great. So what we've done so far is that if we have constraints on LCG outputs, if we observe constraints on these LCG states, we know like an inequality on them. We know it has to be greater than this, but less than that. And if we observe enough of them, we can get enough information to recover the original seed of the LCG. So where do we get these constraints from? Where do we make these observations? One thing you can do in Minecraft is mine a block. And when you mine a block, if you notice, there's kind of an item that drops. And the item falls like in a random direction. So in this case, like this video here, the item falls towards me to the left. Sometimes it could go away from me. Sometimes it could go completely to the left or completely to the right. That is all determined by Minecraft's random number generator. And that information about where the block goes actually tells us information about the LCG outputs. It tells us, okay, the generator generated this number, which caused the block to go in this specific direction. And because of that, we can create these constraints and solve for the original LCG state. But how does that help us? Because remember, the original point of Randar was to find other players on the server. So how does this actually help us? Like, great, we found out what the seed of the world is. How does that help us? So this is where we get into some very interesting code. So when Minecraft generates new chunks, it has to check if a woodland mansion is inside of them. And yes, specifically a woodland mansion. Nothing else, just a woodland mansion. So when it's generating these chunks, each time it generates a new chunk, it'll ask, is there a woodland mansion inside of here? And to do this, it runs like, basically does some stuff with the seed, and it does some checks based on the seed. And if that check is passed, then you have a woodland mansion inside the chunk. Note that what you can't do is store woodland mansion coordinates in a separate file and then just ask that file when you're generating a new chunk, because the kind of point of procedural generation is that it's done independently per each chunk. It's not going to be like you have one like source of truth. You kind of have to like find out where these structures are independently of all the other structures. So that's just kind of how procedural generation works. You have to check it each time you go into a new chunk. But what Minecraft did is some pretty sloppy spaghetti coding practice. So what happens here is that when it's checking if the woodland mansion's inside the chunk, it reseeds the random number generator, like it resets it to your current coordinates. And then it checks if the next random number generated is equal to your current coordinates. And that will happen for some location inside some woodland mansion chunk region. But the important thing here is that they reuse the world random seed, which should be shared across every kind of like random event in Minecraft. They reseeded it for some reason to check for woodland mansions. So basically, this line of code is the culprit. It resets the world seed to your current like location, which is like X and Z and that number. So it resets the seed to your current location. It generates some numbers and checks if the mansion or generates a mansion if those numbers equal your coordinates. So every time you enter a new chunk, the world random seed will be reset just to check for the woodland mansion. So this is like very bad coding practice. If you're doing something like this, just create a new random object. Don't reuse the world random object. And this was fixed in version 1.13 of Minecraft. However, if you've ever been on a server that has been on 1.12 or earlier, and people have like recordings of packets or like replay mod recordings of what goes on in that server, they still have all of this information and they can still find out where you were back in the past when the server used to be on the old version. So it's not entirely fixed in that sense. So yeah, here's kind of like a diagram of what's going on. What it should do is that it should take the world seed and your chunk coordinate, or it should kind of have two RNGs that operate independently. So when your like item drops, it should run on a separate RNG than the one used to generate the woodland mansion, because that one gets reset every time you enter a new chunk. When you mine a block and you want the block to drop, you want that RNG to kind of be independent of everything else. So you want these two RNGs to be separate, and you don't want the block drop RNG to be reseeded every time someone enters a new chunk. So that's the way it should be done. But Minecraft put them in the same RNG. So this seeds the RNG, which influences this. So then you can kind of work backwards by getting this information and finding out the coordinates of every person entering a new chunk. So the exploit basically works by you first mine a block and you observe how the item falls. Then you use lattice methods to determine the random state of the LCG. And then you kind of step backwards in the LCG to find out what the like woodland mansion location seed is. And that's the location of some random person on your server. Any person in the world could have caused that seed to be reseeded. And then you can just see like which chunks are being loaded and you can track players' movements. So here's kind of an example of someone running the exploit. As you can see, There's a lot of like trails being generated, which represents like players moving around and loading new chunks. And yeah, they got all this information just by mining a block and observing how it falls. How do I? Okay, so that was basically the basics of the exploit. There's a lot of details that I didn't get into. Like for example, how exactly do you perform the lattice attack? Because there is a lot of like math detail that goes into there. Also, how do you know how much exactly to step forward or backward the LCG once you get like the block dropping? Like when the block drops, how do you know how many steps backward to go and find what the Woodland Mansion seed is? There's actually a really interesting answer to this. Um, Also, how do we generate the Woodland Mansion seed of the LCG based on our current chunk coordinates? Because if you remember, when you enter a new chunk, you are asking if there's a Woodland Mansion there. And by doing that, you're seeding their RNG. How exactly does that seeding work? There's also a really interesting answer for there. Um, and a bunch of other interesting implementation details. So you can read more at the link there. It's basically a link to the GitHub repo of the exploit. And I mainly based the talk based off that the README in there. Also, you should check out Matthew Bolon on YouTube. He does a lot about like math in Minecraft and like how speedrunners can exploit it and like interesting things that you can do with math results in Minecraft. So, any questions about the exploit? I think I'm done then. Yeah.
Thank you, Arnav, for your talk. Before we get into lab groups, I'd just like to say we have a feedback form here. You can fill out the feedback form whenever and just give feedback on, meeting a specific meeting or cyber lab in general or cyber in general. But yeah. And then also for cyber lab, here is the attendance form and the code is Minecraft. So I'll give you all a couple minutes to fill out the form. Okay, it looks like all phones are down. If you didn't quite get the form, it's the same form that we always use, and also you can ask your lab leads to provide it to you. So now we're going to split off into our lab groups. As usual, if you are in AI, you come up to the front in here. If you are in AdBlock lab, you come up to the front over there. If you are TLS lab, you're back there. And if you are fuzzing, you're out in the hallway going to the clubhouse with Benson. Yeah, you all can get into your groups now.